The Soleil is, here you have a view, is a joint partnership between several agencies, and I mentioned already most of them, which are CNRS and CA, which are the operators of shareholders. Actually, we have the status of a private company. So we have shareholders, and the shareholders are CNRS and CA. The construction has been funded for a large part by the region Île-de-France and by the department of Essonne. We got also some funding from the region Centre, which is the region around Orléans and Tours in France, and from, of course, from, a little bit from the ministry also. Now, you may not be familiar with a synchrotron, so I'll tell you in a very few words what is a synchrotron. And our name is Soleil, which means sun, which means light. And this is our business. We have one business at all synchrotrons around the world. We are producing light. How are we producing light? And why is this light particularly useful for science and industry? Okay, they put, it's just from project to reality. This is Soleil, view from a plane. Now this is a synchrotron, but I'll start with this. We produce light by a phenomenon that was discovered in the middle of the 20th century, and this is when electrons are traveling very fast, and all electrons are traveling, and that's the same in all synchrotrons, practically at the speed of light. It's not exactly the speed of light, and you know, if you were to make a race between light and our electrons, and they go to the moon and come back, light will win by 13 meters. So it's not quite the speed of light, but it's very, very close. And at that speed, the electrons are so-called relativistic. That is, the phenomenon is when they are, the travel is banded by a magnet, they will change their direction, and they will lose some energy by emitting light. And this was actually a problem initially. Synchrotrons started in high energy physics, and that was a byproduct they were not interested in. That was actually, they were losing energy, so it was bad for them. But there are scientists still working with us that were at that time, and during the weekends they were going on the magnet to get the light and do some experiments, because that light has properties which are very useful. The first one is very brilliant. We produce a lot of photons. I mean, photons are the particles of light, or the units of light. So we have high brilliance, we produce a lot of light. It's also polarized and pulsated. That I won't go into the details, it's interesting for some experiments. It is a white light, which means that it covers a very broad spectrum of energy. We are used to white light in the visible range, and with the synchrotron, we cover 100 times more energy than the visible light, and we cover the visible light as well. That's why we call it white. So it covers a very broad range of energies from infrared to X-rays, and we'll see examples of application of all of these energies. And also, it's also a very stable source of light, and the difference, for example, between a laser and a synchrotron is that the synchrotron produces light at a single energy. We produce light on the very, very broad spectrum. So we can do the other types of experiments. So I'll come back to this one. How do we produce light? Practically, we have a device in which we have an electron gun. Your old TV had an electron gun, and it's almost the same. So it just emits electrons, which are accelerated. On your TV, it goes to the screen, produces light, actually. So you can see. Here, we boost the energy to a much higher level. So at the end of the electron gun, which is called the linear accelerator, it's 110 mega electron volts. That's millions of volts, if I may compare it. Then it's boosted in what we call the booster, and then they are injected in what we call the storage ring. Their energy is of 2.75 giga electron volts. So you can, as a comparison, 2.75 billion volts, if you want to put it that way. And there they are stored, and they go through various devices, bending magnets, and every time they move, they emit light. We also now have devices which are put to increase. Instead of just bending once, we have trains of magnets, so the electrons go, and every time they move, they emit light, and it's amplified, so we get 1,000 times more light in doing so. We call that insertion devices, and you will see some of them. And then we have the beam lines, at which, you know, which are outside of the ring, so the electrons go, turn around. At every turn, they receive a little kick of energy to compensate what is lost by emission of light. And so we have a continuous emission of light at all our stations, and we have a capacity of about 40 stations. At the moment, we're still in the construction phase, and we have at the level of 11 beam lines are operational, and we have 15 which are under construction at various stages. So this is what you see. This is a beam of light. Actually, what you see is not the actual light. What you see is the effect of the beam on the atmosphere, and that also emits light like it does in ordinary, not bulb, but you know, those neon type of devices. Now this is the spectrum. These are all the energies going from radio antenna, laser, low infrared, hard X-rays to particle accelerators, radioactive sensor, gamma ray. So what we're covering is basically from infrared to hard X-rays. And what do we do with light? Well, I may ask you the question, what do you do with light? What do you do with light? I show you this. Tell me what it is. You mean it's a metal stick, right? You have done two operations. One is an image analysis, and by that you know it's a stick, and you have done a chemical analysis by spectroscopy. I tell you, because what you have recognized is the reflection of light, and it emits something which is metal. You know it's metal, and you can probably give more characteristics. We do exactly the same, except we don't do that only in visible light, but throughout that energy range, we do that with light which is much, much brighter than, especially in dim environment here, it's not very, it's not a lot of light, but with a lot of light, and we do it on a very, very tiny spaces. So we can analyze small objects or big objects, but essentially we do two things. We analyze forms, we determine what are the shapes of the objects, and then we do the surface analysis or the in-depth analysis to determine what they are composed of, what is the status of that. I mean, you can say, I mean, this is a metal which is not oxidized. I mean, if it was oxidized, you would say, well, it's rusted, right? You would do that, and you know, you would have made the analysis by spectroscopy that that metal is rusted. So you know it's an oxide of iron. So we do exactly the same type of analysis, and I'll show you some examples. But basically, that's what we do. We take light, we look at the objects, and each beam line is now different, because you may want to look in this part of the spectrum, and we have beam lines that are dedicated to look at hard X-rays, so-called soft X-rays, ultraviolet, visible light, and infrared. So we cover the entire range, and we'll have different information. I mean, in the infrared, you see the vibration of the molecules, and if you go into hard X-rays, you will look more at the electronic status of the various layers. I mean, there we come into the chemistry of the atoms. But you will just look at different aspects from, and also then the objects are different. You may want to look at a big object, a tooth, or a big piece of art, for example. It's things that we do. Then you need a special support, and you need an environment. Or you may want to look, that's my own field, I come from biology, so I apologize if many examples I'll take are from biology. You may want to look inside of a cell. Then you need a very thin beam to look to get the analysis of a single point. And I'll show you an example. Now, as I said, we have many beamlines. This is the schematic drawing of all the beamlines that are existing in green and planned in white. I won't go into the details, but this is how it looks like. But you will see one, so I won't go into the details. Before I give you some results, or show you some examples, here are some numbers. The total budget from 2002 to 2012, assuming that everything goes fine after our discussions with the ministry, will be 634 million euros. It's a lot of money. The investment, this is in euros at value 2008. That's today's value. I mean, we've adjusted because, because of the length of the construction, so if you were in current euros, it would be more difficult to compare. The total investment is 277 million euros. The functioning, which is excluding salaries, is 100 million euros, and the salaries for that same period is 257 euros. And we got funding from all these agencies at various ratios. I won't go into the details. After the finish of the construction, the yearly budget will be in the range of 61 million euros. These are the figures, so it's a big operation. But with that, we can have a lot of experiments done. We can do simultaneously 24 experiments, 26 experiments will be when we will be in full operation, 24 hours a day when we are running. So the actual cost of a single 8-hour period, which is called a shift, is in the range of 4,500 euros, which is time where you can do a real experiment. So when it comes to the actual experiment, it's expensive, but it's not that expensive.
How big is the ring?
The ring is, I have a blank, it was 354 meters. Right? It was in the, sorry. It's here. It should be written somewhere. Anyway, I know my number. 354. Now that's the experimental hole. You will see that, and I'll just give you one, maybe two examples of experiments that have been done on our beamline. We had a beamline which was in Switzerland. We built it on the Swiss synchrotron, or we are building the synchrotron here to have it ready. So it's been in operation for 2.5 years, 3 years in Willingen in Switzerland, and now it's just moved to Soleil. And the experiment I'll show you is from this beamline. And what they looked at is not before it's Christmas, almost Christmas, I'll use that example, but is on Pecten Maximus, which is the king scallop. And when you may want to look at the shell of a king scallop. Why would you want to look at the shell of a king scallop? You will look at different elements, calcium, magnesium, and sulfur. And then you do the analysis spotlight stopper. So your actual shell is this. And you look at the concentration of each of these elements in all the layers of the king scallop shell. This would be for magnesium, and this would be for sulfur. So what? I mean, you may ask that question, why is that interesting? Well, that is interesting because, I mean, scallops are in seawater, and they stay where they are, and they grow at a single space. And by the law of chemistry, the deposition of minerals is temperature sensitive. So what you have here is actually a thermometer of the temperature of the water during the period of the growth of the sea scallop. So this is very important. I mean, today we ask a lot of questions about the environment, and as those of you, I don't know if you were in the room yesterday, a wonderful talk by a colleague from Seattle, and he showed all the effects of temperature in the water. I mean, here we have a way to get back the information on water temperature at a given spot. So this is a type of experiment which is at the same time interesting because it tells us about scallop, but also about environment of that scallop. This is a continuation of that same experiment. This is another experiment, and I'll finish there because it's a beamline that you will not see. It's data collected from a beamline which is called swing, and it's small angle X-ray diffraction. Now, I won't go into the details, but what it does in this experiment, you take a solution of a protein that in principle you don't know, I mean you know a little bit about it, but you don't know its shape. And with that curve here, by predicting you can, and this is a remarkable way of calculation, but this is the actual result. It shows you this is the shape of that actual molecule in solution. And the line next to it, which is Proxima 1, that you will visit, so I won't give you an example of that, you can determine on a crystal, this is in solution, you can determine on a crystal the structure, the details, the atomic structure of a given molecule. So if you take that part, for example, you can get its structure and then you can fit it in here. So mixing the two techniques, you get information on the detailed structure and then you can infer what's happening actually in solution, which is closer to the real life than a crystal. So these are complementary type of experiments. And of course, this, I don't know what this molecule is because it's of pharmaceutical importance. So we are not allowed to say, even we don't know because they didn't tell us. We just did the experiment. But the results are so good, I can guess what it is. This is completely different experiment. Just I think this is the last one. This is an experiment which was done on glasses to understand the composition and the chemistry and the evolution of glasses. And this is done at high temperature. Now, how do you reach high temperature? Well, the way it's done, it's a little bead, which is about 1 millimeter. If I manage, I can actually show you how it works. And that bead, no, we don't get the animation, is levitated under a flux of gas and put in front of the X-ray beam, and then what you get is the spectrum at each temperature. And so you can follow, I'm sorry, I don't know, probably we haven't taken the film in the right file, so I won't lose your time. What you see here is a spectrum, and you can record it at all the temperature. You have a laser that warms it up. It's maintained because it's too hot to be in any container. It's maintained in levitation, and then you have the beam, and you do the analysis at all the temperature, and therefore you can follow the process of melting of the glass, which is a very important experiment to understand the way glass is done. So I think last piece of information, we are only one out of 45 synchrotrons roughly that exist around the world, of which there are about 15, close to 20 if I include those that are under construction, third generation light sources. Around us, of course, in France is the European synchrotron in Grenoble, which is shared by 14 countries. In UK, we have Diamond. In Spain, we have Alba, which is under construction. In Germany, there are two third generation synchrotrons, one in Hamburg, one in Berlin. In Italy, there is one in Trieste, Elettra. In Switzerland, there is one in Zurich. There is also one in Lund. And then there are others, of course, in North America. In Far East, the largest one is actually in Japan. There is one in Brazil. And I'll finish with one which is still under construction, and we are quite involved with that. And this is, I want to mention it, it's a story I like very much. It's a project Sesame. Sesame is a synchrotron light source for the Middle East. And it was just, there was a first inauguration, and I was there because we had a lot of interaction with them for many reasons. I can explain if you want. It's being built near Amman, and the partners are, of course, Jordan, the Palestinian Authority, Israel, Cyprus, Turkey, Iran, Pakistan, who did I forget? There is one emirate, I don't remember which one, Egypt. That's about it. But the idea is to say that science goes over the borders and over the local problems, and that you can do science all together. And it was very impressive being at the inauguration, because the ministers from many of these countries were all present and discussing how to fund. It's not completely achieved yet. They're still missing 15 million to get their budget rounded up, but they're on their way. They have the building, they have the elements, and now they need more efforts and support to get to the final aim, which is have that light source of hope, I may say, in the Middle East. Well, thank you. This is a brief presentation. I hope I haven't been too long.